Hello there, and welcome to the Sleepy Science Society. Tonight, we're drifting into the vast expanse of galaxies, those magnificent island universes scattered across the cosmic ocean. As you settle into your pillow and let the day's tension melt away, we'll explore these enormous collections of stars, gas, dust, and mystery that paint the darkness of space with light and wonder. If you find comfort in these gentle journeys through science, I invite you to like this video and subscribe to the channel. It helps other curious souls find their way here, one peaceful night at a time. But for now, all you need to do is rest. Let your breathing slow. Allow your body to sink deeper into comfort. Let your mind float freely among the stars as we begin our exploration of galaxies. When you look up at the night sky on a clear evening, far from the glow of city lights, you might see a faint band of luminescence stretching across the darkness like spilled milk. The ancient Greeks called it Galaxies Kyklos, the Milky Circle, and from this we get our word galaxy. That band is our view into the disk of our own galaxy, the Milky Way, seen from our position within it. Every single star you can see with your naked eye belongs to this galaxy, our cosmic home. But the Milky Way is just one galaxy among an almost incomprehensible multitude. Recent estimates suggest that the observable universe contains somewhere around 2 trillion galaxies, though this number continues to be refined as our instruments improve and our understanding deepens. 2 trillion separate cosmic cities, each one a vast congregation of matter held together by gravity, each one containing its own population of stars, its own clouds of gas and dust, its own story written across billions of years. Galaxies come in an astonishing variety of shapes and sizes. Some are majestic spirals, with graceful arms curving outward from a central bulge, pinwheels of light spinning through the void. Others are smooth, featureless ellipsoids, like cosmic eggs containing ancient stars. Still others defy easy classification, their shapes twisted and irregular, perhaps caught in the middle of some dramatic transformation, or still bearing the scars of ancient collisions. The distances between galaxies are so immense that even traveling at the speed of light, it would take millions or even billions of years to journey from one to another. Yet, despite these vast separations, galaxies are not randomly scattered through space. They cluster together in groups and larger structures, forming a cosmic web of filaments and sheets separated by enormous voids where few galaxies dwell. This large-scale structure tells a story about how the universe evolved, how tiny ripples in the fabric of space and time grew over billions of years into the magnificent architecture we observe today. As we embark on this journey through galactic space, we'll encounter supermassive black holes lurking at galactic centers, mysterious dark matter that outweighs all visible matter, and clouds of gas where new stars are constantly being born. We'll witness galaxies colliding and merging, their shapes transforming over cosmic timescales. We'll peer into our own galactic home and discover our place within it. And we'll contemplate the sheer scale of cosmic structure, from the smallest dwarf galaxies containing millions of stars to giant ellipticals harboring trillions. So, breathe deeply, relax completely, and let's drift together through the realm of galaxies. The story of galaxies begins with the story of the universe itself. Around 13.8 billion years ago, everything we can observe today emerged from an incredibly hot, dense state in the event we call the Big Bang. In those first moments, the universe was nearly uniform, filled with a hot soup of fundamental particles and radiation. But nearly uniform is not the same as perfectly uniform. Tiny quantum fluctuations, perhaps amplified by a brief period of exponential expansion called cosmic inflation, created slight variations in density. Some regions were ever so slightly denser than their surroundings, while others were slightly less dense. These variations were incredibly small, differences of only about 1 part in 100,000, but they were enough. As the universe expanded and cooled, these density variations became the seeds of all cosmic structure. The slightly denser regions contained a bit more matter, and that extra matter exerted a bit more gravitational pull on its surroundings. This gravitational attraction drew in even more matter, causing the dense regions to become denser still. Meanwhile, the less dense regions became relatively emptier as their matter was pulled toward the overdense areas. This process, called gravitational instability, started slowly but accelerated over time. The gravitational pull of the denser regions grew stronger as more matter accumulated, creating a feedback loop that carved the universe into an increasingly lumpy distribution of matter. But there's a crucial detail in this story that makes galaxy formation possible at all. The matter doing most of the gravitational work in those early times was not the ordinary matter that makes up stars, planets, and our bodies. It was dark matter, a mysterious substance that interacts with gravity but not with light. Dark matter dominates the matter content of the universe, outweighing ordinary matter by about 6 to 1. In the early universe, ordinary matter was still coupled to radiation through constant interactions. The coupling created pressure that resisted gravitational collapse, especially on smaller scales. Radiation pressure acted like a cosmic wind, smoothing out variations in ordinary matter and preventing it from clumping together efficiently. Dark matter, however, feels no such pressure. It interacts only through gravity, which meant that dark matter could begin collapsing into clumps and filaments much earlier than ordinary matter. As the universe expanded and cooled, dark matter began forming a complex network of structures, a cosmic scaffolding upon which galaxies would eventually form. These dark matter concentrations created deep gravitational wells, invisible valleys in the fabric of space-time. As ordinary matter finally decoupled from radiation about 380,000 years after the Big Bang, it found itself in a universe already shaped by dark matter. The ordinary matter, primarily hydrogen and helium gas, began falling into those gravitational wells, gathering in the places where dark matter had already concentrated. Over hundreds of millions of years, the gas falling into dark matter halos became dense enough and hot enough for stars to ignite. The first stars were likely massive, short-lived giants that formed from pristine hydrogen and helium, elements forged in the Big Bang itself. These early stars lived fast and died young, many exploding as supernovae that enriched their surroundings with heavier elements created in their cores and during their explosive deaths. slowly, star by star, the first galaxies began to shine. These early galaxies were probably small and irregular, quite different from the grand spirals and smooth ellipticals we see in the nearby universe today. They were the building blocks from which larger galaxies would grow. Two competing models describe how galaxies might have assembled from these beginnings. The first, called the top-down scenario, suggests that massive galaxies formed through the rapid collapse of large gas clouds. In this picture, a single enormous cloud of gas and dark matter would collapse quickly, converting virtually all its gas into stars in a relatively short burst of activity. The resulting galaxy would then evolve slowly as its stars aged. The second model, the bottom-up or hierarchical scenario, proposes that galaxies grew through mergers. Small galaxies formed first, and these smaller systems then collided and merged to create progressively larger galaxies over cosmic time. This process continues to the present day, making galaxy formation an ongoing phenomenon rather than an event confined to the distant past. Evidence supports both scenarios playing roles in the cosmic story. The detection of luminous quasars in the very early universe, less than 1 billion years after the Big Bang, suggests that at least some massive structures formed quickly through processes resembling the top-down model. These quasars are powered by supermassive black holes containing millions or billions of solar masses, and the existence of such massive black holes so early in cosmic history implies rapid assembly of their host galaxies. On the other hand, observations of galaxy mergers throughout cosmic history, combined with computer simulations showing how dark matter halos merge hierarchically, strongly support the bottom-up scenario for most galaxies. The truth appears to be that both processes occurred, with the relative importance of each varying depending on the environment and the particular galaxy in question. As structure continued to form, small dark matter halos merged to create larger ones, and the galaxies they hosted merged as well. These mergers could be violent affairs, with shock waves rippling through the gas, triggering intense bursts of star formation as clouds collided and compressed. Other mergers were gentler, with smaller galaxies being slowly torn apart by the gravity of larger companions, their stars redistributed into streams and shells. Through countless such events over billions of years, the galaxy population evolved, with irregular galaxies becoming less common and larger, more organized spirals and ellipticals becoming more prevalent. The universe transformed from a realm dominated by small, chaotic star systems into one filled with the diverse, majestic galaxies we observe today. When astronomers began systematically studying galaxies in the early 20th century, they noticed that these cosmic islands came in distinct types. Edwin Hubble, working at the Mount Wilson Observatory in California, developed a classification scheme based on the visual appearance of galaxies. His system, still used today with modifications, divides galaxies into 3 broad categories, each with its own subcategories, creating what is known as the Hubble sequence or the tuning fork diagram, due to its distinctive shape when drawn out. The first major category comprises spiral galaxies, and these are perhaps the most iconic and recognizable. Spiral galaxies are characterized by a flat, rotating disk containing spiral arms that curve outward from a central bulge. These arms are not rigid structures rotating like the vanes of a fan. Instead, they are density waves, regions where stars, gas, and dust bunch together temporarily as they orbit the galactic center. Imagine cars on a highway slowing down at a traffic jam. The jam itself moves slowly, but individual cars pass through it at higher speeds. Similarly, stars and gas clouds move through spiral arms, spending time compressed within them before emerging on the other side. While material passes through the arms themselves persist as patterns, giving spiral galaxies their characteristic pinwheel appearance. The spiral arms are sites of vigorous star formation. As gas clouds enter the dense environment of a spiral arm, they are compressed by the increased density and gravity. This compression can trigger the collapse of gas clouds into dense knots that ignite as new stars. The most massive of these young stars are hot and blue, burning their fuel rapidly and shining brilliantly for just a few million years before exploding as supernovae. These brilliant blue stars trace the spiral arms, making them stand out clearly in photographs. Between the arms, the disk contains older, cooler stars whose yellowish light is less dramatic, but represents the steady background population of the galaxy. At the center of a spiral galaxy lies the bulge, a spherical or ellipsoidal concentration of stars. Unlike the disk, which is actively forming new stars, the bulge typically contains older stellar populations. The stars here orbit in random directions rather than in the orderly rotation of the disk, giving the bulge a more chaotic, three-dimensional character. Surrounding the visible disk is the halo, an even larger, more diffuse region containing old stars and globular clusters. These globular clusters are dense, spherical swarms of up to 1 million stars, orbiting the galactic center like satellites. The halo extends far beyond the visible edge of the disk and contains a large fraction of the galaxy's dark matter, which exerts the gravitational pull necessary to hold the galaxy together. Spiral galaxies can be further subdivided. Some spirals have tightly wound arms and large central bulges, while others have loosely wound arms and smaller bulges. An important subclass is the barred spiral galaxy, which has a linear bar structure running through its center with spiral arms emerging from the ends of the bar rather than directly from the core. About 2/3 of all spiral galaxies, including our own Milky Way, are barred spirals. The presence of a bar indicates that the galaxy has reached a certain level of maturity, and the bar itself plays important dynamical roles, channeling gas toward the central regions and affecting star formation patterns. The second major category of galaxies is the elliptical class. Elliptical galaxies range in shape from nearly spherical to highly elongated, like cosmic footballs. Unlike spirals with their organized rotation and distinct structures, ellipticals are smooth and featureless. They lack the spiral arms, prominent dust lanes, and active star-forming regions that characterize spirals. Instead, ellipticals are dominated by older, redder stars orbiting the galactic center in random directions. This gives them their smooth appearance and also means they contain relatively little gas and dust. With little raw material for star formation, elliptical galaxies produce few new stars, and their stellar populations age gracefully without being refreshed by young, hot stars. Elliptical galaxies are classified by how elongated they appear, with designations from E0 for nearly circular to E7 for highly elongated. The largest galaxies in the universe are ellipticals, particularly a subclass called CD galaxies found at the centers of massive galaxy clusters. These giant ellipticals can be hundreds of thousands of light-years across and contain trillions of stars, dwarfing even large spiral galaxies like the Milky Way. At the other extreme are dwarf ellipticals, small galaxies only a few thousand light-years across containing millions rather than billions of stars. Despite their small size, dwarf ellipticals are numerous and make up a significant fraction of galaxies in the universe. How do elliptical galaxies form? The evidence strongly suggests that most ellipticals are the products of galaxy mergers. When two spiral galaxies collide and merge under their mutual gravitational attraction, the orderly rotation of their disks is disrupted. Stars from both galaxies are flung into chaotic orbits, and the spiral arms and disk structures are destroyed. What emerges from this cosmic train wreck is typically a smooth, elliptical galaxy. The merger process also triggers intense star formation as gas clouds collide. But once the merger is complete and the gas is exhausted or dispersed, star formation ceases. The resulting elliptical galaxy settles into a long, quiet old age with little activity beyond the slow evolution of its stellar population. Between spirals and ellipticals lies a transitional class called lenticular galaxies. These galaxies have a disk and a central bulge like spirals, but lack prominent spiral arms. They also contain little gas and dust and show minimal star formation, resembling ellipticals in this respect. Lenticular galaxies might represent spirals that have exhausted or lost their gas supply, perhaps through interactions with other galaxies or with hot gas in galaxy clusters. Alternatively, they might be ellipticals that retained some disk-like structure from their formation. Their intermediate nature makes them valuable for understanding how galaxies evolve from one type to another. Finally, there are irregular galaxies which lack the organized structure of spirals or the smooth appearance of ellipticals. Irregular galaxies often look chaotic and asymmetric, sometimes resembling torn clouds rather than well-defined systems. Many irregulars are small, but they can contain significant amounts of gas and dust, and can host active star formation. Some irregular galaxies are genuinely young systems still in the process of settling into a more organized form. Others are the products of interactions or mergers, their shapes distorted by gravitational forces from nearby companions. The Magellanic Clouds, satellite galaxies orbiting the Milky Way and visible from the southern hemisphere, are classified as irregular galaxies and provide nearby examples of this diverse class. Beyond these main categories exist numerous peculiar galaxies that don't fit neatly into any classification. Ring galaxies display a circular ring of stars and gas surrounding a relatively empty core, possibly formed when a smaller galaxy plunged through the center of a larger one, sending a ripple of matter outward like a splash in a pond. Shell galaxies, a subset of ellipticals, show concentric shells of stars in their outer regions, likely the remains of smaller galaxies that were torn apart and consumed. These exotic forms remind us that galaxies are not static objects, but dynamic systems constantly shaped by their interactions and their environments. We live inside a galaxy, which makes studying our own Milky Way both easier and more difficult than studying distant galaxies. We have the advantage of being immersed in it, able to study individual stars, star clusters, and gas clouds in exquisite detail. But we also lack the external perspective that would allow us to see the galaxy's overall shape and structure at a glance. It's like trying to understand the layout of a forest when you're standing among the trees. Through careful observation and indirect inference, astronomers have gradually pieced together a comprehensive picture of our galactic home. The Milky Way is a barred spiral galaxy, a vast disk-shaped structure about 100,000 light-years across, but only about 1,000 light-years thick through most of its extent. This disk contains the majority of the galaxy's ordinary matter, including stars, gas, and dust. Embedded within the disk are the spiral arms, at least 4 major ones, which wind their way around the galactic center. These arms are named the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm, after the constellations in which they appear most prominently from our viewpoint. The arms contain most of the galaxy's molecular clouds, the dense regions of gas where new stars form, and they glow with the light of young, hot stars born from those clouds. Our solar system resides not in one of the main spiral arms, but in a smaller structure called the Orion Spur or Orion Arm, a minor branch connecting the Perseus and Sagittarius arms. We sit about 26,000 light-years from the galactic center, roughly halfway out to the edge of the visible disk. This location places us in a relatively quiet suburban region of the galaxy, away from the crowded, chaotic environment near the core and far from the sparse outer reaches. The Sun, carrying the Earth and the other planets with it, orbits the galactic center at a speed of about 220 kilometers per second, completing one orbit approximately every 225 million years. This immense orbital period means that since the Sun formed about 4.5 billion years ago, it has completed only about 20 orbits around the galaxy. Since the age of the dinosaurs, we've traveled only about halfway around the galaxy. At the center of the Milky Way lies the galactic bulge, a densely packed region shaped like a bar that extends several thousand light-years along one axis through the galactic center. This central bar, invisible from our position within the disk due to obscuring dust clouds, affects the dynamics of the entire galaxy. It channels gas toward the center, influences the pattern of the spiral arms, and shapes the orbits of stars throughout the inner galaxy. The bulge contains primarily old stars, formed in the early history of the galaxy, and it hosts a population of globular clusters. Those ancient, densely packed stellar swarms that orbit through the galaxy like miniature satellite galaxies. Beyond the visible disk extends the galactic halo, a roughly spherical region that envelopes the entire galaxy. The halo contains old stars, more globular clusters, and very little gas or dust. The stellar populations in the halo move on orbits that take them high above and below the plane of the disk, and they represent some of the oldest stars in the galaxy, formed during the Milky Way's earliest days. But the halo's most significant component is invisible. The dark matter halo extends far beyond the visible galaxy, perhaps reaching distances of several 100,000 light-years from the center. This dark matter provides the gravitational framework that holds the Milky Way together, preventing the rapidly rotating disk from flying apart into space. When we look up at the night sky and see the Milky Way as a band of light, we're looking edge-on into the disk of our galaxy. The band appears brightest toward the constellation Sagittarius because that direction points toward the galactic center, where stars are most densely concentrated. Unfortunately, this view is heavily obscured by dark lanes of dust, blocking visible light from the inner galaxy. However, infrared and radio observations can penetrate the dust, revealing the structure hidden behind the veil. In the opposite direction, toward the constellation Auriga, we look outward through the disk toward the edge of the galaxy and beyond into intergalactic space. The Milky Way is a massive galaxy by local standards, containing somewhere between 100 and 400 billion stars, depending on how you count the faint, low-mass stars that dominate the stellar population by number, but contribute little to the total light. The galaxy's total mass, including dark matter, is estimated at roughly 1 trillion times the mass of the Sun. Despite containing hundreds of billions of stars, the Milky Way also harbors vast clouds of gas and dust, the raw material for future generations of stars. These clouds are concentrated in the spiral arms and in molecular cloud complexes, huge structures that can span hundreds of light years and contain enough matter to form hundreds of thousands of stars. Between the stars lies the interstellar medium, a tenuous mixture of gas and dust that fills the space within the galaxy. Although extremely diffuse by everyday standards, with densities far lower than the best vacuum achievable in terrestrial laboratories, this medium plays crucial roles in galactic evolution. The gas, primarily hydrogen, with some helium, and trace amounts of heavier elements, serves as the reservoir from which stars form. In some regions, this gas is cold and molecular, clustered into dense clouds where chemistry can occur and molecules like carbon monoxide form. In other regions, it exists as warm atomic hydrogen, neutral atoms drifting through space. In still other volumes, particularly around hot young stars, and in the aftermath of supernovae, the gas is ionized into a plasma, stripped of electrons and heated to thousands or millions of degrees. The dust, composed of tiny grains of silicates and carbon compounds, represents only about 1% of the interstellar medium's mass. Yet, it exercises influence far beyond this small fraction. These microscopic particles, typically less than a micrometer across, absorb and scatter starlight, particularly at shorter wavelengths. This selective absorption means that blue light is blocked more efficiently than red light, causing stars viewed through dust to appear redder than they actually are, a phenomenon called interstellar reddening. The accumulated dust creates the dark lanes visible in images of the Milky Way, obscuring our view of the galactic center and inner disk at visible wavelengths. Yet dust is not merely an obstacle. It plays essential roles in the formation of stars and planets. Within cold molecular clouds, dust grains shield the interior from harsh ultraviolet radiation that would otherwise heat and disperse the gas, preventing collapse. The surfaces of dust grains also provide sites where atoms can meet and combine into molecules, catalyzing chemical reactions that would be too slow in the gas phase alone. When stars eventually form within these dusty cocoons, the leftover dust in the disk around the young star provides the material from which planets, asteroids, and comets can grow, accreting grain by grain into progressively larger bodies. This cosmic recycling system is essential to understanding the galaxy's life cycle, and indeed the origin of everything familiar in our world. Stars form from interstellar clouds, igniting nuclear fusion in their cores that converts hydrogen into helium, and, in more massive stars, progressively heavier elements up through iron. These stellar furnaces create the carbon in your cells, the oxygen you breathe, the calcium in your bones, and the iron in your blood. When stars die, they return this enriched material to space. Low-mass stars like the Sun shed their outer layers as planetary nebulae, beautiful, expanding shells of glowing gas enriched with carbon, nitrogen, and oxygen, forged during the star's lifetime. Massive stars meet more violent ends, exploding as supernovae that forge elements heavier than iron in the intensity of the explosion itself and blast them into the surrounding medium along with the elements created during the star's life. This returned material joins the interstellar medium, where it mixes with pristine gas left over from the Big Bang. Given time, gravity pulls this mixed material into new molecular clouds, and the cycle begins again. Each generation of stars is slightly more enriched with heavy elements than the last, a gradual chemical evolution that has proceeded throughout the galaxy's history. The first stars formed from pure hydrogen and helium, containing essentially no heavy elements. The Sun, born about 4.5 billion years ago, formed from gas already enriched by many previous generations of stars, which is why it and the planets contain substantial amounts of elements like carbon, oxygen, silicon, and iron. Every atom in your body heavier than hydrogen was forged inside a star and returned to space through stellar winds or explosive death, later to be incorporated into the molecular cloud that collapsed to form our sun and solar system. You are genuinely made of stardust, assembled from matter recycled through multiple stellar generations over the galaxy's 10 billion-year history. The galaxy itself is the machine that performs this alchemy, transforming the simple hydrogen and helium of the Big Bang into the complex chemistry that makes planets and life possible. Understanding the interstellar medium and the cycles of star formation and death reveals how galaxies transform themselves over time, gradually converting gas into stars and enriching themselves with the products of a stellar nucleosynthesis. At the very heart of the Milky Way, hidden behind thick veils of dust and gas that block visible light, lies one of the galaxy's most mysterious and fascinating objects. This is Sagittarius A star, abbreviated SGAR A star, the supermassive black hole that occupies the galactic center. For decades, astronomers suspected that something massive and compact lurked at the center of our galaxy, but the evidence remained indirect, inferred rather than directly observed. The breakthrough came from patient, meticulous observations of individual stars orbiting near the galactic center. Using advanced telescopes equipped with adaptive optics to compensate for atmospheric blurring, Astronomers tracked these stars over many years, watching them trace elliptical paths around an invisible focal point. One star in particular, designated S2, became crucial to this investigation. S2 orbits remarkably close to the galactic center, completing one orbit in just over 15 years. At its closest approach, called pericenter, S2 sweeps within about 17 light hours of the central object, approaching at nearly 3% of the speed of light. By carefully measuring S2's position over multiple orbits and applying Kepler's laws of orbital motion, astronomers determined the mass and maximum size of the central object. What they found was extraordinary: an object containing approximately 4 million times the mass of the Sun, confined within a region no larger than the orbit of Mercury around the Sun, and possibly much smaller. The density implied by these measurements is so extreme that no known object except a black hole could possess such properties. The term supermassive black hole distinguishes these galactic behemoths from the smaller stellar mass black holes that form when individual massive stars collapse at the end of their lives. Stellar black holes typically contain just a few times the Sun's mass, ranging perhaps from 3 to several dozen solar masses. Supermassive black holes, by contrast, range from millions to tens of billions of solar masses, occupying a completely different regime of mass and size. Sagittarius A star, at about 4 million solar masses, is actually relatively modest for a supermassive black hole. Giant elliptical galaxies can host central black holes exceeding 10 billion solar masses, more than 2,000 times more massive than our galaxy's central black hole. The existence of Sagittarius A star was strongly inferred from stellar orbits and radio observations for many years, but it remained an invisible presence, known only through its gravitational influence on surrounding matter. That changed dramatically in May 2022, when the Event Horizon Telescope collaboration released the first actual image of the black hole, or more precisely, the glowing material orbiting around it. The Event Horizon Telescope is not a single instrument, but rather a global network of radio telescopes synchronized to work together, creating a virtual telescope effectively the size of the Earth. This unprecedented resolution allowed the collaboration to image the immediate vicinity of Sagittarius A star. The image revealed a bright, asymmetric ring of light surrounding a dark shadow, the unmistakable signature of a black hole. This ring is not the black hole itself, which by definition emits no light, but rather hot gas and plasma spiraling around the black hole in what astronomers call an accretion disk. As matter falls toward the black hole from surrounding space, conservation of angular momentum prevents it from falling straight in. Instead, the material forms a rotating disk, spiraling inward like water circling a drain. As this material spirals closer to the black hole, it accelerates to higher and higher speeds, approaching the speed of light in the innermost regions. This acceleration produces tremendous friction and heating. The gas in the accretion disk reaches temperatures of millions or even billions of degrees, so hot that it emits X-rays and gamma rays along with visible and radio light. The matter becomes a plasma, completely ionized with electrons stripped from nuclei. Magnetic fields thread through this plasma, creating complex dynamics and sometimes launching narrow beams of matter and energy away from the black hole in jets. Some of this superheated matter eventually crosses the event horizon, the point of no return beyond which nothing, not even light, can escape the black hole's gravitational pull and disappears forever from our universe, adding to the black hole's mass. The dark region, visible in the center of the image, is larger than the event horizon itself, a consequence of the black hole's extreme gravity bending light rays. Light, attempting to pass close to the black hole, is deflected by curved spacetime, and light aimed too close is captured entirely, unable to escape. This creates a shadow that extends well beyond the actual event horizon, a dark circle approximately 2.5 times the diameter of the horizon itself. The bright ring surrounding this shadow represents light from the accretion disk, including light emitted from behind the black hole that has been bent around it by the warped spacetime, allowing us to see the far side of the disk as well as the near side. Despite its immense mass and the dramatic appearance of its accretion disk, Sagittarius A star is currently quite quiet compared to the most active supermassive black holes in the universe. It accretes matter only sporadically, perhaps swallowing the occasional gas cloud or unlucky star that wanders it too close. But most of the time it feeds slowly, like a cosmic grazer rather than a voracious predator. This results in relatively dim emission, detectable primarily in radio waves and infrared light, with occasional brighter flares when something substantial falls in. This quiescent state stands in stark contrast to active galactic nuclei, or AGN, found in many other galaxies across the universe. In an AGN, the supermassive black hole voraciously consumes surrounding matter, creating an accretion disk so luminous that it can outshine the combined light of all the stars in the galaxy. The most extreme AGN are called quasars, short for quasi-stellar objects, because they appear almost point-like in images despite being powered by regions smaller than our solar system. Quasars are visible across most of the observable universe, with some of the most distant lying more than 13 billion light-years away, appearing as they were when the universe was less than 1 billion years old. The existence of such massive, luminous black holes so early in cosmic history poses intriguing questions about how they grew so large so quickly. Some AGN launch enormous jets of matter and energy, narrow beams that extend far beyond the host galaxy, sometimes reaching millions of light-years into intergalactic space. These jets are powered by the black hole's rotation and by magnetic fields threading through the accretion disk. Material in the jets moves at nearly the speed of light, and when this relativistic plasma eventually slows and interacts with the tenuous intergalactic medium, it creates enormous lobes that emit radio waves, making these jets visible to radio telescopes. These jets can have profound effects on their host galaxies, heating and dispersing gas that would otherwise cool and form stars, effectively regulating galaxy growth. The Milky Way's central black hole was likely more active in the past than it is today. Observations of molecular clouds near the galactic center reveal evidence of ancient outbursts, periods perhaps a few million years ago when Sagittarius A star consumed a large amount of matter and blazed with luminosity hundreds or thousands of times greater than today. These past outbursts left their mark on surrounding gas, ionizing it, and creating bubbles and structures still visible today. Though dramatic by our standards, even these outbursts were far less powerful than the jets seen in the most extreme active galaxies. Still, they remind us that our galaxy's center is not entirely peaceful, and that Sagittarius A star could potentially awaken again if circumstances provided it with sufficient fuel. The relationship between supermassive black holes and their host galaxies is one of the most intriguing areas of modern astrophysics. Observations reveal tight correlations between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its bulge and the velocities of stars within it. This correlation suggests that black holes and galaxies co-evolve, growing together through cosmic time. Exactly how this happens remains a topic of active research. One possibility is that galaxy mergers, which bring large amounts of gas to galactic centers, feed the black hole and trigger episodes of rapid growth. The energy released by the feeding black hole then affects the surrounding galaxy, heating gas, and perhaps preventing further star formation. This feedback mechanism might explain why the most massive elliptical galaxies, which presumably grew through many mergers, contain such massive black holes and show so little ongoing star formation. The black hole's energy output may have effectively shut down star formation by dispersing or heating the galaxy's gas supply. Not all galaxies contain supermassive black holes of equal size. Observations suggest that nearly every large galaxy harbors a supermassive black hole at its center, but the masses vary considerably. Small, low-mass galaxies might have black holes containing only thousands or millions of solar masses, while giant ellipticals can host monsters with billions of solar masses. The supermassive black holes in spiral galaxies tend to be smaller than those in ellipticals of comparable stellar mass, possibly because spirals form stars more continuously and merge less frequently than ellipticals, leaving less opportunity for their black holes to grow through accretion and mergers. The existence of supermassive black holes in the early universe, less than 1 billion years after the Big Bang, presents a puzzle. How did these black holes grow so massive so quickly? Several theories have been proposed. Perhaps black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar black hole stage entirely. Or maybe the first generations of supermassive stars, far more massive than any stars in the present-day universe, collapsed to form black holes that then grew rapidly by accreting surrounding gas. Whatever the mechanism, the presence of billion solar mass black holes in young galaxies tells us that black holes can grow extremely rapidly under the right conditions. To understand galaxies fully, we must confront one of the most profound mysteries in all of science: the fact that most of their mass is completely invisible. The visible stars, glowing gas clouds, and dust lanes that we can observe directly through telescopes account for only a small fraction of a galaxy's total mass. The rest, the overwhelming majority, is dark matter, a mysterious substance that does not emit, absorb, or reflect light. We detect dark matter only through its gravitational effects on visible matter, yet its presence is undeniable and its influence on cosmic structure absolutely fundamental. The evidence for dark matter is overwhelming and comes from multiple independent observations and techniques all converging on the same inescapable conclusion that galaxies, and indeed the entire universe, are dominated by an unseen component we have yet to identify. One of the earliest and most compelling pieces of evidence came from studying the rotation curves of spiral galaxies in the 1970s and 80s. Astronomer Vera Rubin and her colleagues made careful measurements of how fast stars and gas clouds orbit in spiral galaxies as a function of distance from the galactic center. According to Newtonian mechanics, if most of a galaxy's mass were concentrated in the bright central bulge and visible disk, orbital speeds should decrease with distance from the center, following the same pattern planets follow in our solar system, where distant planets orbit more slowly than inner ones. The Sun's gravitational pull weakens with distance, and orbital speed decreases correspondingly as you move outward through the solar system. But the observations showed something completely different and unexpected. Instead of declining, orbital speeds in spiral galaxies remain roughly constant or even increase slightly with distance, extending far beyond the edge of the visible disk into regions where few stars shine. These flat rotation curves can only be explained if galaxies are embedded in much larger halos of invisible matter, whose gravity keeps the outer regions moving faster than the visible matter alone could account for. The mass of this dark matter halo typically exceeds the mass of all the visible stars, gas, and dust combined, sometimes by factors of 10 or more. The dark matter extends far beyond the visible galaxy, creating a roughly spherical distribution that dwarfs the luminous disk and bulge nested within it. Gravitational lensing provides another independent and powerful line of evidence for dark matter's existence. Einstein's general theory of relativity predicts that mass warps the fabric of spacetime, and this warping deflects the paths of light rays passing nearby, an effect called gravitational lensing. When light from a distant background galaxy passes near a massive foreground galaxy or galaxy cluster, the foreground object's gravity bends the light, distorting and often magnifying the image of the background galaxy. In some cases, the lensing creates multiple images of the same background object, or stretches it into beautiful arcs that curve around the lensing mass. By carefully analyzing these distortions, measuring exactly how much the light has been bent, astronomers can map the distribution of mass in the foreground lensing object with remarkable precision. The results consistently reveal far more mass than can be accounted for by visible stars, gas, and dust. The inferred mass distribution matches beautifully with what we would expect for halos of dark matter surrounding the visible galaxies, providing completely independent confirmation that this dark matter is real and distributed in specific ways. Some of the most dramatic and convincing examples come from colliding galaxy clusters. Cosmic train wrecks, where two massive clusters have smashed together at speeds of thousands of kilometers per second. In these collisions, the visible gas in each cluster, which outweighs the stars and makes up most of the normal matter, collides with gas from the other cluster and is slowed by the collision, like two opposing winds meeting and creating turbulence. This gas emits X-rays due to its high temperature, allowing it to be mapped. The galaxies themselves, being much smaller than the distances between them, pass through the collision largely unscathed, like bees from two swarms interpenetrating with few actual collisions. And the dark matter, which interacts only weakly, if at all, with ordinary matter, passes through essentially unimpeded, feeling only gravity. By using gravitational lensing to map where the mass is located, and X-ray observations to map where the hot gas is located, astronomers can see that in these colliding clusters, the majority of the mass has separated from the visible gas. The famous bullet cluster provides perhaps the clearest example. In this system, the bulk of the mass, mapped through gravitational lensing, lies in two separate clumps that pass through each other during the collision, while the hot gas, visible in X-rays, is concentrated between them where the two gas clouds collided and were slowed. This clean separation of mass from visible matter provides smoking gun evidence that dark matter exists and behaves differently from ordinary matter, passing through the collision while the gas is affected. What is dark matter? Despite decades of intense theoretical speculation and experimental searching, we still don't know for certain, and this ignorance represents one of the most embarrassing gaps in our understanding of the physical universe. The mystery is profound because dark matter is not some minor footnote in cosmic accounting. It outweighs ordinary matter by approximately 6-to-1 throughout the universe. Everything we can see, every star, every galaxy, every glowing gas cloud, every living being, all the ordinary atoms that we're familiar with, constitutes less than 1/6 of the total matter content. The rest is dark matter, and we don't know what it's made of. It's not simply ordinary matter that happens to be dark, like planets, asteroids, brown dwarfs, or even black holes, because there simply isn't enough of that material to account for the observations, and such objects would reveal themselves in other ways. Instead, dark matter appears to be something fundamentally new, a type of particle, or perhaps a family of particles that interacts with ordinary matter and radiation only through gravity, remaining invisible to telescopes because it neither emits nor absorbs light at any wavelength. Physicists have proposed numerous candidates for dark matter particles. One popular class of candidates comprises weakly interacting massive particles, or WIMPs, hypothetical particles that would have been produced in enormous numbers in the hot early universe, and would interact only through gravity and the weak nuclear force, not through electromagnetism. Another candidate is the axion, originally proposed to solve a problem in particle physics, but which could, under the right conditions, also serve as dark matter. More exotic possibilities include primordial black holes formed in the very early universe, sterile neutrinos that interact even more weakly than the known neutrinos, or even modifications to the laws of gravity itself that would mimic the effects we attribute to dark matter, though this last possibility has difficulty explaining all the observations, particularly the behavior seen in colliding clusters. Numerous experiments around the world are searching for dark matter particles, attempting to detect them directly as they stream through Earth or looking for the products of dark matter particle collisions or decays. These experiments use ultra-sensitive detectors shielded deep underground to block interference from cosmic rays and other background radiation. So far, despite decades of searching with increasingly sensitive instruments, these direct detection experiments have not produced a confirmed detection of dark matter particles. Each null result rules out certain types of particles and narrows the parameter space where dark matter might hide, but the particle's true nature remains elusive. This absence of detection doesn't mean dark matter doesn't exist. The gravitational evidence is too strong, but it does mean that dark matter is even more elusive than many physicists hoped. Perhaps dark matter particles interact so weakly with ordinary matter that they will never be directly detected in laboratories, only inferred through their gravitational effects. Or perhaps dark matter is something we haven't imagined yet, a phenomenon requiring new physics beyond our current theories. Despite its elusiveness, dark matter plays absolutely crucial roles in galaxy formation and evolution. As we discussed earlier, dark matter began clumping under gravity before ordinary matter could, creating the gravitational scaffolding upon which galaxies formed. Without dark matter, the observable universe would be a very different place. Computer simulations that include dark matter produce cosmic structures that match observations beautifully, with filaments, walls, and voids filled with galaxies distributed in patterns matching what telescopes reveal. Simulations without dark matter fail to produce these structures, yielding a universe far more uniform and less interesting than the one we inhabit. Recent research has revealed intriguing connections between dark matter content and galactic properties. One study found that the masses of supermassive black holes correlate more strongly with the dark matter halo mass than with the visible galaxy's properties alone. This suggests that dark matter, though invisible and aloof, somehow influences even the growth of black holes at galactic centers. Another line of research examines galaxies that appear to contain very little dark matter, puzzling anomalies that challenge our understanding. If confirmed, these galaxies might form through unique processes, perhaps being stripped of their dark matter halos through interactions with larger galaxies. The typical dark matter halo extends far beyond the visible galaxy, reaching perhaps several 100,000 light-years from the center. This halo is roughly spherical, though simulations suggest it might be somewhat flattened or triaxial in shape. The density of dark matter is highest near the center and decreases smoothly with distance, though the exact profile remains uncertain. At the position of our Sun in the Milky Way, dark matter contributes about half the total mass density, with ordinary matter making up the other half. Closer to the galactic center, ordinary matter dominates, while in the outer halo, dark matter is essentially all there is. Throughout the galaxy, dark matter provides the gravitational glue that holds everything together, preventing the rapidly rotating disk from flying apart and anchoring the orbits of satellite galaxies and globular clusters. Galaxies are not static objects frozen in time. They evolve, change, merge, and transform over billions of years. Understanding this evolution is one of the central goals of extragalactic astronomy. By observing galaxies at different distances and therefore at different times in the past. Because light takes time to reach us, astronomers can piece together how the galaxy population has changed over cosmic history. The picture that emerges is one of continuous transformation driven by mergers, star formation, and feedback processes. In the early universe, more than 10 billion years ago, when the cosmos was only a few billion years old, galaxies looked quite different from those nearby today. The early universe was dominated by small, irregular galaxies undergoing intense star formation. These galaxies were rich in gas, and they converted that gas into stars at prodigious rates, far higher than the star formation rates in present-day galaxies. The light from these distant galaxies is dominated by young, hot, blue stars, giving them a distinctive appearance that astronomers refer to as blue and star-forming. Images of the very distant universe, such as those captured by the Hubble Space Telescope in its deep field observations, reveal these galaxies as small, often irregular blobs of light scattered across the sky. Over cosmic time, these small galaxies merged to form larger ones. As we've discussed, the bottom-up hierarchical model of galaxy formation predicts exactly this behavior. Smaller dark matter halos and their associated galaxies merge to form larger systems, and this process continues throughout cosmic history. When two galaxies merge, several dramatic processes unfold over hundreds of millions of years. If both galaxies contain significant amounts of gas, which is typical for spiral galaxies, the collision can compress this gas violently. Imagine two enormous clouds interpenetrating, their gas contents meeting and colliding even as the stars within each galaxy pass by each other largely unscathed. The distances between individual stars are so vast compared to the stars' sizes that actual stellar collisions are extraordinarily rare. Two galaxies can completely merge without a single star in one actually hitting a star in the other. But gas is different. Gas clouds can and do collide, and when they do, shock waves ripple through them, compressing the material and triggering intense bursts of star formation. These collision-induced starbursts can convert gas into stars at rates hundreds or even thousands of times higher than the steady star formation rates in normal spiral galaxies like the Milky Way. A starburst galaxy might form stars at the rates of hundreds of solar masses per year, compared to the Milky Way's modest 2 to 3 solar masses per year. At such extreme rates, even a gas-rich galaxy exhausts its fuel supply in mere tens of millions of years, a cosmic eye blink. The resulting galaxies blaze with the combined light of countless young, hot, massive stars, and they glow intensely in infrared light as dust throughout the galaxy absorbs visible and ultraviolet starlight and re-radiates it at longer wavelengths. Some of the most luminous galaxies in the universe are dusty starburst systems undergoing or recently completing major mergers. The merger also fundamentally disrupts the structure of both participating galaxies through gravitational forces. Tidal forces, arising from the fact that different parts of each galaxy experience different gravitational pulls from the other galaxy, stretch and distort both systems. Long tidal tails of stars, gas, and dark matter can be pulled out, extending for hundreds of thousands of light-years beyond the main bodies of the galaxies. These tails form beautiful, ephemeral structures visible in deep images of interacting systems, resembling cosmic antennae or bridges connecting the merging galaxies. Computer simulations can reproduce these shapes with remarkable fidelity, confirming our understanding of the gravitational processes at work. As the merger proceeds and the two galactic cores spiral closer together, dynamical friction slows their approach. Dynamical friction arises because each core, passing through the other galaxy's halo of stars and dark matter, gravitationally attracts material, creating an overdense wake behind it. The gravitational pull of this wake acts like a drag force, gradually removing energy and angular momentum from the core's orbit and causing it to spiral inward. Eventually, perhaps after several close passages where the cores whip around each other in ever-tightening ellipses, they merge into a single central concentration. The final product of a major merger between two gas-rich spirals typically resembles an elliptical galaxy rather than a spiral. The orderly rotation of the disks has been scrambled into random stellar orbits. The spiral arms, those delicate density wave patterns, are destroyed. Stars that once moved in nearly circular orbits within a flat disk now follow chaotic trajectories that can take them high above and far below the merged system's center. The resulting galaxy is smooth and featureless, lacking the spiral structure, prominent dust lanes, and ongoing star formation that characterize spirals. This transformation from spiral to elliptical helps explain why elliptical galaxies dominate the populations of dense galaxy clusters, where mergers are more common, while spirals remain more prevalent in less dense environments where galaxies can evolve in relative isolation for longer periods. Not all mergers involve equal-sized galaxies colliding. Often, a large galaxy encounters a much smaller companion, perhaps a dwarf galaxy containing only millions or billions of stars, compared to the hundreds of billions in a giant. In these unequal mergers, the smaller galaxy is gradually torn apart by tidal forces from the larger companion, its stars stripped away and assimilated into the larger galaxy's halo. This process, called galactic cannibalism or minor merging, allows giant galaxies to grow steadily over time, accumulating mass from numerous small victims. The remnants of cannibalized galaxies can sometimes still be seen as stellar streams, thin ribbons of stars arcing through the halo of the larger galaxy, temporary scars marking ancient meals. The Milky Way itself has consumed numerous small galaxies over its history, and is currently in the process of tidally disrupting several dwarf companions. The Sagittarius dwarf elliptical galaxy, located on the far side of our galaxy from us, is slowly being shredded by the Milky Way's gravitational field. Its stars are being pulled into long streams that wrap around our galaxy like ribbons, gradually merging into the Milky Way's halo population. Other dwarf galaxies in orbit around the Milky Way face similar fates, their orbits decaying over time until they too are torn apart and consumed. This ongoing cannibalism represents the Milky Way's continued growth through minor mergers, a gentler version of the dramatic collisions between large spirals. Looking ahead several billion years, we can predict with reasonable confidence that the Milky Way faces a more dramatic merger in its future. The Andromeda Galaxy, our nearest large neighbor, lies about 2.5 million light-years away and is approaching us at roughly 100 kilometers per second. Despite the enormous distance separating our galaxies, gravity is pulling them together, and observations of Andromeda's motion across the sky confirm that we are on a collision course. In approximately 4 billion years, the Milky Way and Andromeda will begin their merger, a cosmic collision that will transform both galaxies utterly. A key question in galaxy evolution is what turns off star formation. As we've seen, many elliptical galaxies and some spirals contain little gas and show minimal star formation despite containing vast numbers of old stars. something must have removed the gas or prevented it from cooling and collapsing to form new stars. Astronomers call this process quenching, and understanding it is crucial to explaining the galaxy population. Several mechanisms might contribute to quenching. In dense galaxy clusters, the hot gas surrounding galaxies can strip away their cold gas reservoirs, a process called ram pressure stripping. Alternatively, energy from supernova explosions or winds from massive stars might heat the gas and blow it out of the galaxy altogether, especially in smaller systems where the escape velocity is lower. Active galactic nuclei provide another powerful quenching mechanism. As we discussed, the supermassive black hole at a galaxy's center can release enormous amounts of energy when actively accreting matter. This energy heats and disperses surrounding gas, potentially shutting down star formation across the entire galaxy. This AGN feedback is thought to be particularly important in massive elliptical galaxy, where observations suggest that star formation shut down relatively quickly after major mergers. The energy from the central black hole prevents gas from cooling and collapsing, maintaining the galaxy in a quiescent state for billions of years. Observations reveal an interesting pattern called downsizing. In the early universe, the most vigorous star formation occurred in massive galaxies. Over time, star formation has gradually shifted toward less massive systems. Today, the most massive elliptical galaxies form essentially no new stars, while smaller spirals continue to convert gas into stars at modest but steady rates. This downsizing pattern challenges simple hierarchical models that predict small galaxies should form stars first. The resolution appears to involve feedback processes that suppress star formation in massive galaxies more effectively than in smaller ones, possibly because massive galaxies host more powerful AGN and stronger supernova-driven winds. Looking ahead, we can predict some aspects of future galactic evolution. The Milky Way and the Andromeda Galaxy, our nearest large neighbor, are approaching each other and will collide and merge in about 4 billion years. Despite both galaxies containing hundreds of billions of stars, direct stellar collisions will be extraordinarily rare because stars are so small compared to the distances between them. However, the gravitational interaction will be dramatic, distorting both galaxies, triggering bursts of star formation, and eventually merging them into a single, larger elliptical galaxy that some have dubbed Milky Way. The Sun and Earth, if they still exist, will be flung into new orbits within this merged system, but they will likely survive the collision unharmed, simply finding themselves in a very different galactic neighborhood. Galaxies do not exist in isolation, but rather form a grand cosmic architecture spanning the observable universe. This large-scale structure resembles a vast cosmic web, with galaxies distributed along filaments and sheets that surround enormous voids. Understanding this structure and how it formed is one of the triumphs of modern cosmology, connecting the physics of the early universe to the distribution of galaxies we observe today. The story begins with those tiny quantum fluctuations we mentioned earlier, variations in density that were imprinted on the universe during inflation. After inflation ended and the universe continued to expand and cool, these density fluctuations became slightly overdense and underdense regions in the distribution of dark matter and ordinary matter. As we've discussed, Gravity amplified these variations over time. The overdense regions attracted more matter, growing denser, while underdense regions emptied out as their matter was pulled away. This gravitational instability carved the universe into an increasingly complex pattern. Computer simulations have become essential tools for understanding structure formation. These simulations start with the initial conditions inferred from observations of the cosmic microwave background radiation and then evolve forward in time, following billions of dark matter particles as gravity pulls them together. The results are stunning. The simulations produce filaments, walls, and voids that match the observed distribution of galaxies remarkably well. The dark matter first collapses into filaments, one-dimensional threads stretching across millions of light years. Where filaments intersect, knots of dark matter form, creating particularly dense regions. Ordinary matter falls into these dark matter structures, and it is here that galaxies form and cluster together. The cosmic web is hierarchical, with structure on multiple scales. On the smallest scales, individual galaxies orbit within small groups. The Milky Way, for instance, belongs to the local group, a collection of about 80 galaxies dominated by the Milky Way and Andromeda, with numerous smaller dwarf galaxies orbiting these two giants. The local group is roughly 10 million light-years across, a modest structure by cosmic standards. On larger scales, groups merge into clusters, which can contain hundreds or even thousands of galaxies bound together by their mutual gravity. Galaxy clusters are among the largest bound structures in the universe. A rich cluster might span several million light-years and contain a total mass equivalent to 10,000 trillion suns. The galaxies in a cluster move rapidly, their velocities held in check only by the cluster's immense gravitational pull. Between the galaxies, the cluster contains hot, X-ray emitting gas, typically far more massive than all the visible stars combined. This hot gas fills the space between galaxies, and its temperature, often tens of millions of degrees, reveals the depth of the cluster's gravitational well. Only such a massive structure could hold on to gas at these extreme temperatures. The nearest large galaxy cluster to us is the Virgo cluster, located about 50 million light-years away. The Virgo cluster contains over 1,000 galaxies and is dominated by giant ellipticals, including the famous galaxy M87-7, which hosts one of the most massive, supermassive black holes known. The local group, along with several nearby groups and smaller clusters, are all falling toward the Virgo cluster, drawn by its enormous gravity. But even the Virgo cluster is part of a larger structure, the Virgo supercluster, which spans over 100 million light-years and contains tens of thousands of galaxies. Recent mapping efforts have revealed even larger structures. The Laniakea supercluster, identified through careful analysis of galactic motions, encompasses the Virgo supercluster and numerous others, spanning more than 500 million light-years. The Milky Way resides near the edge of Laniakea, slowly flowing along with surrounding galaxies toward a region of particularly high density called the Great Attractor. These enormous structures are not gravitationally bound in the traditional sense because the expansion of the universe is pulling them apart even as their internal gravity tries to hold them together. Nevertheless, they represent real, coherent structures in the cosmic web. Between these filaments and clusters lie the cosmic voids, vast regions containing very few galaxies. These voids can span hundreds of millions of light years, representing the largest structures in the universe. Far from being truly empty, voids contain sparse distributions of galaxies and dark matter, but at densities far below the cosmic average. The voids formed as matter drained out of underdense regions and toward overdense ones. Over billions of years, this process created the foam-like structure we observe, with galaxies concentrated on the surfaces of bubbles surrounding evacuated interiors. The large-scale structure of the universe encodes information about cosmology and fundamental physics. The sizes and distributions of these structures depend on the total amount of matter in the universe, the balance between dark matter and ordinary matter, the properties of dark energy driving cosmic acceleration, and the nature of those initial fluctuations imprinted during inflation. By carefully measuring the clustering of galaxies on various scales, astronomers can constrain these cosmological parameters with impressive precision. The current consensus, called the Lambda CDM model, incorporates cold dark matter and a cosmological constant, or dark energy. And it successfully explains observations ranging from the cosmic microwave background to the distribution of galaxies across billions of light years. Looking out to large distances means looking back in time, because light travels at a finite speed. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, when the universe was much younger. This ability to look into the past allows astronomers to study how structure evolved over cosmic history. Observations confirm that the universe was indeed more uniform in the past, with less pronounced clustering, and that structure has grown hierarchically as predicted, with small structures merging to form larger ones over time. Within galaxies, stars are born from clouds of gas and dust, in a process that has repeated countless times throughout cosmic history. Understanding where and how this star formation occurs illuminates the life cycles of galaxies, the chemical evolution of matter, and ultimately the origins of planets and life itself. The process begins in the cold, dense molecular clouds that permeate the disks of galaxies, particularly concentrated in spiral arms where compression helps trigger the collapse of gas into new generations of stars. Molecular clouds are enormous structures by any human standard, often spanning hundreds of light-years across and containing enough mass to form thousands, tens of thousands, or even millions of stars. Yet despite their immense size, these clouds are extremely cold, typically hovering just 10 to 30 degrees above absolute zero, temperatures cold enough to freeze nearly any substance solid. At these frigid temperatures and in the relative density found deep within the clouds, atoms can come together to form molecules, a rarity in the harsh environment of interstellar space. Molecular hydrogen, consisting of two hydrogen atoms bound together, becomes the dominant constituent, though other molecules, including carbon monoxide, ammonia, water, and even complex organic compounds can form in smaller quantities. Dust grains, those microscopic particles of silicates and carbon compounds we've mentioned, mixed throughout the cloud play an absolutely critical role in maintaining these conditions. The dust shields the cloud's interior from ultraviolet radiation streaming from hot stars elsewhere in the galaxy. This UV radiation would otherwise heat the gas, increasing the random motions of atoms and molecules and creating pressure that would resist gravitational collapse. By blocking this radiation, dust allows the deepest, densest regions of molecular clouds to remain cold, and still creating conditions where gravity can overcome internal pressure and begin pulling matter together. Within the intricate fractal structures of a molecular cloud, certain regions become denser than others through various processes. Perhaps the cloud passes through a spiral arm, where the overall density of matter is higher and compression occurs. Perhaps a nearby supernova explosion sends a shock wave rippling through the cloud, compressing gas as it passes. Perhaps the cloud simply contains initial density variations that gravity amplifies over time. Whatever the trigger, once a region within the cloud becomes sufficiently dense, perhaps containing several hundred or thousand solar masses in a volume just a few light years across, it begins to collapse under its own gravity. This collapse doesn't happen uniformly or all at once. The cloud fragments into smaller clumps as it falls inward, each clump continuing to contract independently. This fragmentation is crucial because it means that molecular clouds don't form single, unimaginably massive stars. Instead, they form entire clusters or associations of stars simultaneously, with the most massive stars concentrated in the densest regions and lower mass stars scattered more widely. Each collapsing clump grows denser and hotter as gravitational potential energy converts to heat, warming the core of the forming star. The process takes time, measured in hundreds of thousands to millions of years, an eye blink in cosmic terms but an eternity by human standards. Eventually, after sufficient contraction, the core of a collapsing clump becomes so hot and dense that nuclear fusion ignites. Hydrogen nuclei, protons stripped of their electrons by the intense heat, move fast enough to overcome their mutual electric repulsion and fuse together, forming helium and releasing energy in the process. This energy output creates pressure that balances the inward pull of gravity, and the object achieves a stable configuration as a main sequence star, beginning what might be billions of years of steady hydrogen fusion. At the moment of ignition, when fusion first begins, the newborn star often undergoes a vigorous early phase, driving powerful winds that begin to clear away the remaining gas and dust from its immediate vicinity, gradually revealing the star to optical observation after its hidden gestation. This process doesn't happen in isolation. Molecular clouds typically form entire clusters of stars simultaneously, sometimes thousands or even tens of thousands of stars being born in the same enormous cloud over a few million years. The most massive stars, those with dozens or even over 100 times the Sun's mass, form only in the densest central regions where the most material is available. These massive stars are rare but incredibly important. Despite their scarcity, they dominate the light and energy output of young stellar clusters because they are so much more luminous than their low-mass cousins. A single star of 50 solar masses can be 100,000 times more luminous than the Sun, outshining tens of thousands of normal stars combined. These massive stars live fast and die young, burning through their nuclear fuel at prodigious rates. While a star, like the Sun, will fuse hydrogen steadily for about 10 billion years, a massive star exhausts its fuel in just a few million years, sometimes even less. And when these giants die, they die spectacularly. The core collapses catastrophically, and the star explodes in a supernova, one of the most energetic events in the universe. For a brief period, a single supernova can outshine an entire galaxy, and the explosion disperses most of the star's mass, along with heavy elements forged in its core and during the explosion itself, back into the interstellar medium at speeds of thousands or tens of thousands of kilometers per second. These massive stars and their eventual supernova explosions have profound effects on their surroundings and on the galactic environment. Their intense ultraviolet radiation ionizes surrounding gas, creating glowing nebulae, those beautiful clouds of fluorescent gas visible in astronomical images. The radiation pressure and stellar winds from massive stars push against nearby gas, creating expanding bubbles and shells that can extend for dozens or hundreds of light years. When the stars explode as supernovae, the blast waves compress and shock surrounding material, and this compression can actually trigger new waves of star formation in nearby clouds, creating a self-propagating process where one generation of stars triggers the birth of the next. At the same time, these energetic processes can also suppress star formation by heating and dispersing gas, making it too hot and diffuse to collapse under gravity. This creates a complex interplay between positive and negative feedback, where star formation in one region can both trigger and suppress star formation in neighboring areas. The balance between these processes helps determine the overall star formation rate in a galaxy, and shapes the structure we observe in spiral arms and star-forming regions. The supernova explosions also inject tremendous amounts of energy into the interstellar medium, helping to maintain the hot, ionized phase of gas and driving turbulence throughout the galactic disk. Crucially, supernovae and the winds from massive stars enrich the interstellar medium with heavy elements, atoms heavier than hydrogen and helium that astronomers collectively call metals regardless of their chemical properties. The first stars in the universe formed from pure hydrogen and helium, the only elements produced in significant quantities by the Big Bang. These first stars forged heavier elements in their cores through nuclear fusion, building progressively heavier nuclei up through iron. When they exploded, they scattered these elements into space, enriching the gas from which the next generation of stars would form. This cycle has repeated throughout cosmic history, gradually enriching the interstellar medium with heavier and heavier element abundances. The Sun, born about 4.5 billion years ago, formed from gas already enriched by many previous generations of stars. About 2% of the Sun's mass consists of elements heavier than helium, elements that could only have been created in earlier stars and returned to space through stellar winds and supernovae. The planets, including Earth, formed from the same enriched material, which is why they contain substantial amounts of elements like carbon, oxygen, silicon, and iron. Without the element-forging factories of earlier stellar generations, Rocky planets like Earth could not exist, and neither could the complex chemistry that led to life. The calcium in your bones, the iron in your blood, the carbon forming the backbone of every organic molecule in your cells, all of this was forged inside stars that exploded billions of years ago, their ashes eventually incorporated into the molecular cloud that formed our solar system. This interplay between star formation and feedback creates a cycle. Molecular clouds collapse to form stars. The most massive stars quickly die and explode, disrupting the remaining cloud and dispersing much of its gas. The dispersed gas mixes with the ambient interstellar medium, gradually cools, and eventually collects into new molecular clouds where the process begins again. This cycle recurs continuously in actively star-forming galaxies, with new generations of stars enriching the interstellar medium with heavier elements. The Sun and Earth are products of this cycle, formed from gas enriched by many previous generations of stars, which is why we contain elements like carbon, oxygen, and iron that could only have been created in stellar cores. The rate of star formation in a galaxy depends on several factors. Most importantly, the amount and density of cold gas available. Galaxies with abundant cold gas form stars vigorously, while those that have exhausted or lost their gas cease forming stars. In spiral galaxies, star formation is concentrated in the spiral arms and in giant molecular cloud complexes scattered through the disk. The disk environment, with its ongoing gas supply being fed by infall from the halo and recycling of material from dying stars, maintains star formation over billions of years, though the rate gradually declines as gas is consumed or lost. In contrast, elliptical galaxies typically show little or no ongoing star formation. Having exhausted their gas supplies during their formation or lost it through various processes, they lack the raw material to make new stars. Their stellar populations age passively, gradually reddening as the most massive, bluest stars die off and are not replaced. This dichotomy between gas-rich, star-forming spirals and gas-poor quiescent ellipticals is one of the fundamental divisions in the galaxy. Population, though as we've seen, various transitional types and special circumstances create a more nuanced reality. The interstellar medium that permeates galaxies is far from uniform. It exists in multiple phases with vastly different properties. The coldest, densest phase comprises the molecular clouds we've discussed, with temperatures around 10 to 30 degrees above absolute zero. A somewhat warmer, less dense phase consists of neutral atomic hydrogen, traced by radio emission at 21 centimeters wavelength. This atomic gas fills much of a spiral galaxy's disk and extends beyond the visible stars. A hot, ionized phase, heated by supernova explosions and stellar radiation, fills cavities and extends above and below the galactic disk, with temperatures reaching millions of degrees. These different phases coexist in a dynamic equilibrium, with gas constantly transitioning between phases through heating, cooling, compression, and expansion. The dust, mixed with the gas, plays crucial roles despite representing only about 1% of the interstellar medium's mass. Dust grains absorb and scatter starlight, particularly at shorter wavelengths, creating the dark lanes visible in spiral galaxies when seen edge-on. This extinction can be so effective that optical telescopes cannot penetrate to a galaxy's central regions. Infrared observations, however, can see through the dust because longer wavelengths are scattered less effectively. Dust also affects star formation by shielding molecular clouds from disruptive radiation and by catalyzing the formation of molecules on grain surfaces. When stars form within dusty clouds, the dust absorbs their ultraviolet and visible light and re-radiates it at infrared wavelengths, making young stellar regions glow brightly in the infrared, even when hidden at optical wavelengths. Within this diverse galaxy population, certain systems stand out for their extreme properties, pushing our understanding of what galaxies can be and how they behave. These cosmic extremes include some of the most energetic and bizarre objects in the universe. Starburst galaxies convert gas into stars at prodigious rates, often hundreds of times faster than normal spirals like the Milky Way. At these rates, a starburst galaxy exhausts its gas supply in mere tens of millions of years, a blink of an eye cosmically. Starbursts are often triggered by galaxy interactions or mergers that funnel gas toward galactic centers, creating the dense environments where rapid star formation can occur. The resulting galaxies blaze with the light of countless young, hot stars, and glow intensely in infrared light as dust absorbs and re-radiates stellar radiation. Starbursts cannot last long before depleting their fuel, making them transient phases in galactic evolution. Active galactic nuclei represent another extreme. Galaxies whose central black holes are accreting matter so vigorously that they outshine their entire host galaxies, the most luminous AGN or quasars, visible across most of the observable universe. Quasars were more common in the early universe when galaxy mergers were frequent and gas was more abundant, providing ample fuel for black hole growth. Today, nearby galaxies rarely host quasars, though less luminous AGN remain fairly common. Some AGN launch enormous jets of relativistic plasma that extend far beyond the host galaxy, creating double-lobed radio sources millions of light-years across. These radio galaxies, including famous examples like Cygnus A, represent the most energetic sustained phenomena in the universe. Ring galaxies present striking visual oddities, displaying a near-perfect ring of stars surrounding a relatively empty core. These rings are thought to form when a smaller galaxy punches through the disk of a larger one in a nearly head-on collision. The impact sends a density wave rippling outward through the larger galaxy's disk, like a splash in a pond, compressing gas and triggering star formation in an expanding ring. The ring continues expanding and gradually disperses over hundreds of millions of years, making ring galaxies relatively rare because they represent a transient phase. Shell galaxies, typically ellipticals, display concentric shells of stars in their outer regions, visible in deep images. These shells are the remnants of smaller galaxies that were torn apart by tidal forces and consumed. The shells represent where stars from the destroyed galaxy reached their maximum distance before falling back toward the center, creating periodic enhancements in the stellar density. The shells gradually fade as stars disperse throughout the larger galaxy, but they can remain visible for billions of years, providing clues about the merger history of massive ellipticals. Ultra-compact dwarf galaxies represent another curiosity. Objects more massive than typical globular clusters, but more compact than dwarf galaxies. These objects might be the stripped cores of dwarf galaxies that ventured too close to larger galaxies and lost their outer stars to tidal stripping. Alternatively, they might be genuinely massive star clusters formed in intense starbursts. Their nature remains debated, illustrating that galaxies come in forms that blur traditional boundaries between categories. A particularly intriguing recent discovery involves the spiral galaxy designated 2MSX J23453-268, nearly 1 billion light-years distant. This galaxy, roughly 3 times larger than the Milky Way, hosts a supermassive black hole launching radio jets stretching 6 million light-years across space. Such powerful jets are typically associated with elliptical galaxies, not spirals, making this system highly unusual. The galaxy also contains about 10 times more dark matter than the Milky Way, which appears crucial for maintaining its structure while the central black hole rages. This discovery hints that spiral galaxies, including potentially the Milky Way, might under certain circumstances develop powerful AGN that could affect life within them. While our own Sagittarius A star is currently dormant, evidence suggests it was more active in the past, and it could potentially reawaken if fed sufficient matter. The diversity revealed by these extreme systems demonstrates that galaxies are dynamic, evolving entities capable of dramatic transformations. No two galaxies are exactly alike, and rare objects often provide crucial insights into processes that affect all galaxies to varying degrees. One of the most fundamental questions in cosmology is how many galaxies exist. The answer depends somewhat on how you define a galaxy and what you can observe. But recent estimates provide staggering numbers. Early attempts to count galaxies relied on deep images from the Hubble Space Telescope, particularly the deep field observations that stared at tiny patches of sky for days, accumulating light from incredibly distant and faint galaxies. Extrapolating from these deep fields to the entire sky, astronomers initially estimated perhaps 100 to 200 billion galaxies in the observable universe. More recent analysis, accounting for galaxies too faint or distant for current telescopes to detect, has revised this number upward dramatically. A study from 2016, analyzing multiple sources of data and correcting for unobserved galaxies, estimated that the observable universe contains at least 2 trillion galaxies. This represents roughly 10 times more galaxies than older estimates. However, subsequent observations, including data from the New Horizons spacecraft which measured cosmic background light from outside the inner solar system's zodiacal dust, suggest this number might be somewhat high. The true figure likely lies somewhere between several 100 billion and 2 trillion. But regardless of the exact count, the number is almost incomprehensibly large. These galaxies are not uniformly distributed across space or time. Because light travels at finite speed, when we look to greater distances, we look back in time. The Hubble deep fields and similar observations reveal galaxies as they appeared billions of years ago, when the universe was much younger. At very large distances, we see the universe as it was when galaxies were still forming and evolving rapidly. These distant galaxies often appear smaller and more irregular than nearby galaxies, supporting the hierarchical model, where small galaxies merge to form larger ones over time. The most distant galaxies observed lie more than 13 billion light-years away, appearing as they were when the universe was less than 1 billion years old. These early galaxies are typically observed in infrared light because their emitted ultraviolet and visible light has been red-shifted, stretched to longer wavelengths by the expansion of the universe during the light's journey to us. Studying these distant galaxies provides a window into the era when the first stars and galaxies were lighting up the previously dark universe, an epoch astronomers call cosmic dawn. Observations reveal that the overall rate of star formation in the universe has changed dramatically over cosmic history. Star formation peaked when the universe was about 3 billion years old, an era when galaxies were forming stars about 10 times more vigorously on average than galaxies today. Since then, star formation has gradually declined as galaxies have consumed or lost their gas supplies, and as fewer gas-rich mergers occur. This cosmic decline in star formation means the universe is gradually fading, with fewer new stars being born to replace those that die. Billions of years in the future, the universe will be darker than today, filled with aging stellar populations in quiescent galaxies. The observable universe has a finite size, limited by the fact that light has had only a finite time to reach us since the Big Bang. The edge of the observable universe lies about 46 billion light-years away in all directions, making the observable universe roughly 92 billion light-years across. Beyond this horizon, galaxies exist, but their light has not yet had time to reach us. The actual universe might extend far beyond what we can observe, possibly infinitely far. But we can never see beyond the cosmic horizon imposed by the finite age of the universe and the speed of light. Within that observable volume lie those trillions of galaxies, each a universe unto itself, unreachable by any conceivable technology, but connected to us through the light they emit and the cosmic web of gravity and structure they inhabit. As we drift toward the end of this journey through the realm of galaxies, let your mind rest gently on what we've explored together. Galaxies are not merely collections of stars scattered randomly through space. They are intricate, evolving structures, shaped by gravity, dark matter, and the flow of gas and energy across billions of years. From the smallest dwarf galaxies to giant ellipticals, from peaceful spirals to violently active quasars, the diversity of galaxies reflects the rich tapestry of processes operating across cosmic scales. We've seen how galaxies formed from tiny quantum ripples, how dark matter provides the invisible scaffolding for cosmic structure, how supermassive black holes grow alongside their host galaxies and influence their evolution. We've explored our own Milky Way, a magnificent spiral containing hundreds of billions of stars including our Sun, with a supermassive black hole at its heart and spiral arms rich with star-forming clouds. We've witnessed galaxies colliding and merging, transforming spirals into ellipticals, and we've contemplated the vast cosmic web of filaments and voids that organizes galaxies across the observable universe. The story of galaxies is ultimately our story too. We live inside a galaxy, our Sun one star among hundreds of billions, our planet. A tiny world orbiting that star. every atom in our bodies was forged in stars and scattered through space by supernova explosions, later gathered into the cloud that formed our solar system. We are quite literally made of stardust, assembled by cosmic processes playing out over billions of years. Looking up at the night sky and seeing that faint band of the Milky Way, you're looking at your cosmic home from the inside, seeing the combined light of distant stars sharing our galactic neighborhood. Galaxies also remind us of how much remains unknown. Dark matter dominates galactic masses, yet remains mysterious and undetected. Supermassive black holes lurk at galactic centers, their formation and growth still not fully understood. The relationship between galaxies and the cosmic web, the mechanisms that regulate star formation, the ultimate fate of galaxies in an accelerating universe, all these questions drive ongoing research. Each new telescope, each new observation, reveals unexpected phenomena and raises new questions, ensuring that the study of galaxies remains one of the most vibrant and exciting fields in all of science. If you've enjoyed this peaceful journey through galaxies and the cosmic structures they inhabit, I invite you to like this video and subscribe to Sleepy Science Society. Your support helps these gentle explorations of science reach other curious minds seeking both knowledge and rest. Feel free to share your thoughts or favorite galactic facts in the comments below. Each comment, each like, help build this community of sleepy science enthusiasts. For now, simply let these cosmic images fade softly from your mind. You don't need to hold on to any specific facts or figures. Let them dissolve like stars fading into dawn. What remains is a quiet sense of wonder, an appreciation for the immense scales and deep time involved in galactic evolution, and perhaps a new perspective on our place in the cosmos. We are small, yes, but we are connected to everything around us through billions of years of cosmic history. Every breath you take contains atoms that were once inside stars, scattered across light years, and eventually gathered here on Earth. Let your breathing slow and deepen. Feel your body sinking into comfort, heavy and relaxed. Your eyes can close if they haven't already. The galaxies spin on through space without needing your attention. The cosmic web stretches across billions of light years, patient and eternal. You can rest now. Let go of effort, let go of thought, and simply drift into peaceful sleep, cradled by the same gravity that shapes galaxies, part of the same universe that has unfolded over nearly 14 billion years into the magnificent structures we've explored tonight. The night is yours. Rest well, stargazer. Sweet dreams among the galaxies.